native. So it's my great pleasure to introduce Ted Briscoe, who's Professor of Computational Linguistics at Cambridge, published variously over a very long and illustrious career.
Certainly long, anyway.
Has also done a lot in industry, so co-founded and is CEO of, and do I pronounce it Ilexa, however I like, which has in itself spun out various companies, including SwiftKey, that people may have heard of, which was very successful. So, as someone who's really taken NLP and demonstrated its commercial utility at a time when perhaps it wasn't as evident as it is nowadays. It's also the inaugural director of the Alta Institute, as you're seeing on your slides, and in 2014 co-founded the English Language iTutoring Limited, and was its chief scientist until 2019, which was then bought out by Cambridge Assessment. Is that right? I think so. And has lost his slides. See, you moved. I told you.
Well, no, it went at the time up. But the guy pressed something over here to make that. I'm not quite sure what it was.
We've lost the slides now.
No, it's
Were the IT guys down here to help you get?
Yes, and it was doing this to start with, but then he pressed something on here. I don't know what he was pressing. Nothing obvious. Is there? Try stopping and restarting the video.
I think that's the video of you.
Oh, sorry, it timed out and then lost. Thank you.
Tremendous. Thank you for that.
Excuse me, just one more thing. It's started to do funny things with the
certain continuous.
This is not working, but also when I press this, it's not actually. What did you just press to do that?
Command minus.
Command minus, okay, because it's. Okay, thank you. Right, shall I start before it times out again? Thank you for the introduction, and it's a great pleasure to be here. So I'm going to talk today about a fairly applied project which has been running for quite a long time to use machine learning and natural language processing to help with teaching people a foreign language, a second language, but in this case it's going to be English. So we have this thing called the Alta Institute in Cambridge, which is a cross-departmental institute. Alta stands for Automated Language Teaching and Assessment. So the idea is to develop language learning technology, and it involves a speech group as well as the natural language processing group, and also Cambridge English, which is a part of the university that actually certifies people. And last year they certified 5.5 million people for various, various English exams. So this is quite a big effort, and what we're trying to do is support both assessment and also tutoring. Okay, it's a big problem teaching people English because there aren't enough teachers, and most of them are in the wrong parts of the world. So the people who want to learn English are based in China, India, and so on, or many of the teachers are based in the West. So technology actually has the potential, to democratize the process, because at the moment, the wealthy will travel to the US or the UK and pay $1,000 plus to a tutoring college for a few months to learn. Of course, there has been educational technology out there already. So we've got MOOCs and we've got things like online tutoring systems and also adaptive learning systems. And those have been applied to language, but with perhaps less success than they've been applied to things like maths and computer science. Part of the reason is because it's people, in order to learn effectively, people need very good feedback. Maths and computing, it's fairly easy to set up automated feedback that scales. Not so easy with language learning. One obvious exception is Duolingo, who have a pretty successful tutoring system. But how much, how good are those sort of systems that do give some feedback at the moment? Well, in the assessment world, people talk about construct validity. So knowing the language is about speaking, listening, reading, and writing. And typically, all of those activities involve putting together, strings of words or understanding strings of words. Whilst what Duolingo does is essentially really deconstruct this down to closed tests where you're asked to fill in a gap, and you can do that in various ways, either spoken or written. So here's a typical example, which is a real example, not from, I won't say where it came from, but it comes from a very reputable outfit. Can we see gap? The Earth is a globe, and you then are given a choice of things to fill in. The correct answer supposedly is that. But actually, you could put whether in there or if, and actually, if you're sort of geometrically inclined, you might actually say the Earth isn't a globe. So, if or whether might look more appropriate. The problem, of course, is that language just does not work like that. There isn't a single right answer. It's not 2 + 2 = 4. To some extent, the context in which this is being said might determine what the right answer is, but you don't get context with this sort of thing. So although you can learn this way, it's not necessarily the best way to learn. So what we would like to look at is something that has more construct validity. So there is this standard kind of way of assessing people's language attainment, which applies not just to English, but to other languages, which is it's certainly a European standard that has been pretty much adopted worldwide, called the CEFR level. And all of Cambridge's exams are grading you at a particular level. But just giving people summative feedback like that isn't enough if you want them to learn. In a tutoring context, you also need to give them some formative feedback. And what you'd like to do there is sort of point to things that are wrong and scaffold them, improving what they're doing. At the moment, even in these expensive colleges, if people write an assignment, it's usually more than a week before they get feedback, by which time they've kind of forgotten what they were doing anyway. So what we'd like to do is make that feedback happen within seconds and encourage people to keep trying to improve. So that's what I'm going to talk about really is just specifically on writing today. Summative and formative feedback done automatically and done in a way similar to how a good teacher would do it. That's the advantage. That's the idea or the goal. The advantages are that, if you can get iterated grades based on incremental feedback, keep improving, you get a kind of good sense that you're making some progress. It also encourages you to try writing more, which is the way people learn. It's basically a practice-driven activity. And it also reduces teacher load and things like student profiling. So you can profile people on the basis of the kind of errors they're making, the level that they're writing at, et cetera, et cetera. So we built a system called Write and Improve, which is out there and anybody can use. And this is sort of what it looks like. When you come into the system, it says, what's your level? And here's some suggested prompts. This one is, a friend is coming to stay, write them an email saying what's going to happen. And you can see at the top that it's saying that my attempt at this is on target for the prompt. So I'm actually answering the way relevant to the prompt. But you can also see in the text that there are star question marks, which are saying maybe you need a word before the word that's boxed. And there are exclamation marks, which are saying maybe you need to substitute something for this word. And also everything's brown, which means that there are problems other than the ones that have been specifically marked. So in other words, I've done rather a poor job. Unfortunately, the progress summative bit is off the bottom of the slide because apparently I can't use I can't use the display mode and get it on the screen. But what that says is here's a little blue dot which says that you're working at CFR level A1, which means I haven't achieved much yet. Now, if I magically fix all of those errors, which in fact I did over 4 incremental sessions, in order to fix them, I can hover over the words that are boxed, and it gives me some hints. But they're not enough to just fix it. It's not a writing assistant in the same way that Google Docs or Word has writing assistants built in. It's actually much more giving clues. And not all of the things it says are going to be right, because sometimes when you change the context, which is also errorful, then what's marked will become kind of irrelevant. So you still need to think that you get some scaffolding. And you can see that my score is going up in terms of the blue dots here. And you probably can't read the scale, but what it's now saying is that in terms of this little piece of writing, I'm on the A1, A2 boundary. So I've managed to improve my writing. Doesn't mean, of course, that I'm A2 now, because typically a learner doing this might spend 20 minutes to get to this point. It just means in terms of that piece of text that they've manifested, they've managed to improve it to that level. To really go from A1 to A2 is probably going to take them hundreds of hours of work, and more than just practice in the writing system, of course. Okay, so that's just some background. Now I'm going to talk about the technology that we use, first of all, to give the summative assessment, and secondly, to give the formative feedback. So we have access to a thing called the Cambridge Learner Corpus, which is essentially writing exams that have been collected, so a small sample of exams over the last 20 plus years. And those have been manually error-coded with corrections. And they come from all sorts of exams like IELTS that you might use here as a university level exam, Cambridge First that's typically taken by teenagers in schools, and so on. And this is what these scripts look like after they've been transcribed and error-coded, where the green is the correction, and the red is incorrect. And in some cases, we're just inserting text, so it's N for missing. And in some, we're doing replacements. And there are a range of types on these. And so we, in effect, have a good and a bad version of all of these scripts. And what we basically, so this is the process that's gone through. There's a transcription process and then an annotation process. And then we come along and we take the good and the bad versions of these and we parse them with an automatic parser. And we mark things like part of speech. So RR here means an adverb. And these nodes on this tree are telling you something about the syntactic structure underneath. And so this corrected version comes out as a sentence beginning with an adverbial. Here's the incorrect version, and you can see that the tree looks rather different. It says it's a fragment at the top, not a sentence. And there are various rules here which are marked -R, which means that they're rare kind of marked constructions. So and some of the part of speech labels have changed because the guy misspelled low, thought as though, so that comes out as an adverb, which is just a bit off the bottom of the screen here. And we're also doing things like lemmatizing the words, so we know the base form, the dictionary lookup form, if you like, as well. And this is another sort of view on the same kind of thing here. Instead of drawing a tree, we're working out bilexical syntactic relations between words. So this is a piece of speech, it's not learner text. It's just to show you that we could say that anyone is subject to have gone in this particular sentence. And that's quite a long range dependency. So we have these different views of the data that we extract automatically. And then what we can do is we can assess people's competence by using these features as proxies for writing competence. So we're going to use a machine learning model, and the model is going to be trained using this labeled data. And we're going to extract these features from the original data and the pars of the data as well, feed them into an algorithm, and then predict scores based on that. And there's basically three ways we could do this: classification, regression, or ranking. I'm sorry, there's a regression and ranking also disappeared off the bottom of the slide. Maybe if I resize this, or is this dangerous?
Like command and minus again.
Yes, that's better, isn't it? That's much better. We could, in principle, use any one of these. Anybody got any ideas which would be the right method to choose to produce the scores? Well,
Ranking.
Regression, ranking. Well, everybody used regression in previous work, which always struck me as very surprising because there's implicit order. If you've got an ordering of either numbers or labels, like these CFR labels, then you can exploit that in a ranking algorithm directly in a way that you can't in a regression algorithm. So our first sort of contribution to this was to actually show that when you hold all other things equal, ranking does give you a better model. But this is old-fashioned machine learning, where we do a lot of feature extraction. So we spend quite a bit of time figuring out what's the optimal set of features. And then we train a rank preference algorithm where the loss function is you look at pairs, and if you're ordering them the wrong way, you adjust your weights so that you end up ordering them the right way. And if you've got a large data set, you will sample these pairs because there'll be a lot of them. And that way you build a predictive model. And we've essentially always we've done these experiments with SVMs and also a timed aggregate perceptron model, which is not, or wasn't actually in the public domain when we started this work. So just for replicability, we've done both. And what I'm going to report mostly is the SVM. So what about features? What features can you use? Well, you can obviously use word sequences or lemma sequences. You can also use part of speech sequences, and you can use these constructions. So you can pull these rule names out of the parser, and they give you clues. So for example, V1 modal base means somebody has used an auxiliary modal verb like can or might or must or something. And that's indicative of a certain level of attainment in terms of the constructions that you can produce. Furthermore, that kind of feature generalizes better than just looking for words like can or could. So it's a more reliable signal. And there are a lot of other features you can use. Two obvious ones is you can use an error rate estimate. So if you can in some way, say by looking at unseen word sequences and assume that that's an error, you can get an estimate of how much has gone wrong. So you're essentially looking at competence and the performance of that competence and weighing the two against each other. And there are things like readability scores. I've just given a very obvious one, which is the ratio of words to sentences and of syllables to words. But there are many more like this. You can get complexity metrics out of the parser. How complex is this sentence at the syntactic level and so on. So you have a big feature space, and the game is to explore that feature space and find a model that correlates well with humans. So the first thing to note with this is that if two human examiners mark the same script, they will tend to correlate about 0.8 if they're good at it. So that's about your upper bound. And the data that we're training on is produced by humans, so there's inherent noise in the data because we typically only have one score when we're training. And you can see here what this is if you like, an ablation study. First of all, we just see how well we can do with word sequences. Then we add part of speech sequences, then some of these readability metrics, then constructions, and then error rate. And this is just one small experiment. You can do lots of experiments like this, and depending on where on the CFR level you're trying to examine people and so on, different features will play different roles. So you always need to customize a model like this to get a good score. And you can see for this model that it's still not up to the upper bound, but it's not far off the upper bound. And if we just use this as a regression, so we'll keep everything constant, use the same feature set, the same training data, the same test data, and we compare regression to pairwise ranking, you can see that pairwise ranking is actually quite a bit better. So ranking does look like it's the right way to do this. Okay, so now another little question for you. Which one is the automated system amongst these 5 raters? There are 4 examiners, and they're all senior examiners at Cambridge Assessment. They're the people who train other people to do this marking task, and then there's the system. And this is just the first 10 from a data set of about 100, which have been multiply remarked so that we can do this kind of experiment.
Why?
4. Any other guesses?
I also think 4.
Okay, well, we'll go with that. You're wrong, it's 1. So it's just an anecdotal sort of bit of evidence that it's pretty hard to tell the system apart from humans. What you will notice is that the pass mark for this is 23, and it's 2 texts which are marked out at 20 combined together. So this is 2 writing tasks on 1 exam. What you will see is when you get towards the outliers, there's more range, because human examiners are very concerned about whether this is a pass or not, less concerned about the sort of an accurate overall distribution. Although they're asked to do that, what you find is that there's greater diversity at the beginnings and ends of the score range. And of course, they don't use the whole score range either. So in particular, if you look at that one, the system said 12, but one person said 17 and 2 others said 5. That's because it's a failing script and people find it very hard to sort of say how bad it is. Okay, so what kinds of features are highly ranked by these models? Well, mostly it's these construction features because they actually generalize very well. You can see that T-frag is a very good negative signal, but things like using adjectival or adverbial phrases is a very good positive signal. This is in the middle of the CFI level, so it's going from being lower intermediate to upper intermediate, and it would be the kind of test that somebody learning English in a school would take when they're about 14 to 16. And you can see modality is quite important. Things like necessary probably score a bit for using words like that. The people is a very common error that people make because they're confused between people and person, and also article errors. Whether you should put in a the or not, it's confusing for a lot of learners. So again, there's a lot of these features in the system. I'm just showing you some of the top ones so you get a sort of sense of what it learns. Okay, so that's all well, but if you want to deploy this in any kind of non-tutoring context or even tutoring, you'd like to be sure that the system can't be gamed too easily. So very early work in this area was very easy to game. So we can do things like randomly permute things. So we can permute words, single words in a sentence. We can permute phrases of 2 or 3 words. We can also change nouns, just swap nouns around based on speech tags. And we can also reorder the sentences. And what we did is actually ask examiners to mark a whole load of scripts that we built like this from high quality scripts. And they found that quite difficult, but they did do it. And then when we checked for correlation against these marks for these outlier scripts, what we find is that the system is pretty good at spotting all of the kinds of permutations except the very last one, which is permuting sentences. And actually, if you think about what I've told you so far, that makes perfect sense, because I told you that we use a parser that parsers a sentence, and we get features out per sentence. But I haven't told you about any features that really look at the coherence across sentences. So in fact, in the early exams, that's not very important because people write rather short texts like the one I made up and showed you. But when you get to IELTS, things like that, that really is quite important because people are writing sort of 1,000 words for the writing part of the exam. And so there'll be multiple paragraphs and so on. So what can you do about this? Well, we used a sort of very simple technique to measure local coherence between sentences. So if you have two sentence pairs and you have representation of the words which allow you to induce a similarity relation across the words. So in this case, we use something called random indexing and essentially modeled predicted words by their contents using a random indexing algorithm. Then what you get out is vectors that represent the similarity between words according to the context they occur in. And then we can represent local coherence between two sentences as an algorithm that maximizes the coherence of any possible mapping of one set of words to, in the first sentence, to the set of words in the second sentence. And then you basically just take the average of that over the answer, and that gives you a measure of coherence. So now actually that improved for this particular exam at the middle of the range. It improved the overall score when we threw in these outliers, but also more importantly, as you can see in the bottom table, we went from having a very, very poor correlation on these sentence permuted examples to something that's at least sort of reasonable, although still not that good. Problem there is that asking people to mark these things is weird because examiners aren't used to marking things that are automatically permuted in this way. So I think that, you know, you can't take these numbers hugely seriously, but this was our first attempt. So, so far I've told you about a traditional machine learning approach where we combine feature engineering, finding the best set of features, with algorithms like the perceptron or an SVM. But of course, there's been this absolute revolution in the field and indeed in machine learning in general, in that these days, the technique that everybody's exploring is sort of end-to-end deep learning models. So we built an end-to-end, we've actually built quite a few end-to-end deep learning models for this task. I'm just going to tell you about one, which is fairly straightforward. Most of them, I should say, don't beat the baseline, if you like, the old-fashioned way of doing it, because the old-fashioned way of doing it actually does require quite a lot of experimentation and so on. And what you would like is something that doesn't require as much customization, as much experimentation. So it's worth exploring these techniques. The other thing about this technique is we look at the whole text. So we're not looking at it sentence by sentence, we're looking at the whole text. So distill BERT is a transformer, which is the model that everybody is using right now, but it's cut down, it's distilled into a smaller model, which still performs almost as well as the original model. And it's essentially a language model. So it builds word embeddings that are contextualized and good prediction and are good at predicting missing words in data. That's how you build one of these things. And they're trained on a huge amount of data. So then what we're going to do is fine-tune that to this task. Now, in the earlier work, I forgot to say that we can build very good models with about 2,000 scripts. To build a good model here, even for fine-tuning, you need really an order of magnitude more text. So this model I'm going to talk about is 100,000 scripts fed through it. And here we're just using sequence regression. So we have a start label, and we're going to regress on that. And then we have word embeddings for the entire script. So it could be 60, it could be 200 or so, it could be 500, depending on what level people are writing at. Now, if you just train this model and you just regress towards the marks, what it actually learns is that long things are good, because it's trying to learn a representation of the data from scratch. It's not giving any hints about what makes good writing. And the thing that's most manifest is just that long words, long sentences, and long scripts are good. So that's what it learns, because deep learning is just a massive correlation machine. It doesn't have access to causation. But causation of a good writing script is you show, good linguistic performance. So you can use relative clauses without errors, this kind of thing. So how do we bias the model to look in the right possible space for the right kind of information? What we do is we use multitask learning where you have more than one loss function. So your base level loss function is mean squared error against the score. But we introduce a secondary objective. The secondary objective is to label each token in the script with its dependent grammatical relation. So in that example I gave you earlier, we'd be labeling anyone as a subject, and gonna would be the root in that sentence that I showed before. So we're doing like a half parse, and we train that with cross entropy. So you have this combined loss function, which you can weight. I think in the best model, they were just weighted equally. And then you're training on parse text because you need to know what the grammatical relation is. And it's automatically parsed, so we don't need any more labels than just the score manually. But when at runtime, we don't have the parse at all. We can just apply the model directly because we're not really interested in the assignment of the grammatical relations to the tokens. We're interested in the score. But by training with this, what's really an auxiliary loss function, because we're not interested in it at prediction time, we are able to push the model into the right sort of area, learn the right sort of features. And now our correlation compared directly to the TAP model that I was showing you before, or actually not quite that, but a similar sort of model, is a bit better. It's up to 0.78, and the TAP is about 0.75. And if you remember, the baseline is usually, so the upper bound is usually about 0.8 in terms of examiner agreement. Turns out if you take the rounded mean of the two models, because they have slightly different behavior, you get to 0.79. So now you're almost at human and good human level performance. So that looks very promising. But you still need to think about what are the biases in the new model. And it turns out the new model is actually pretty robust permutations of the kind I showed you earlier. And it has, if anything, a stronger bias against the permutations of nouns and prepositions, which is good, actually, because there are a lot of preposition errors, and you would generally expect permutations to reduce the score. And it has a good bias for edits that people have done that improve text. So we can extract text from this rightly improved system and say that if people have improved their text over time, then the scores should go up. And comparing against that, it's actually doing a slightly better job, the neural model. But it still, despite the auxiliary loss training, it favors longer things. So if you just duplicate a text 4 times, it will always score it higher, which is kind of unfortunate because that's an easy way to cheat. And that actually doesn't work in the other model. Much to my surprise, but when I thought about it, I understood it. It deals with punctuation incredibly badly. So if you put in 3 exclamation marks or 3 question marks, you get a better score. If you put in a whole row of asterisks, you get a better score. Why is that? Well, because in general, better texts actually do have more punctuation. But the model treats punctuation as essentially an embedding. It treats a punctuation as like a word. And it therefore doesn't really have a very good model of the difference between punctuation and words. And so it just says, oh, here's some good stuff that I'd seen in good essays. I didn't think of that. I sort of suspected that we were, that there would be all sorts of horrors in this approach, but that one I must admit I didn't think of. So it's good to mix the 2 models because the other model actually, they do complement each other. But now you might want to say, well, is correlation really the right way of thinking about this? Is that the right measure, getting one number out? Because correlation hides all of this kind of stuff that's going on in the background. So maybe we need a better metric. Now, like everything else in my field, there's been a huge fight over how to evaluate this. Nobody's really ever agreed on what would be better than correlation. There's things like quadratic weighted kappa and so on. So we wrote a whole paper about why all these things are flawed. And what we do at the moment is we just look at root mean squared error across the score range. So this is a script made up of 2 writing assignments, and these are the scores that are being assigned by, this is actually a live test. There were 16 examiners with about 300 scripts, and the blue line is their scores, their root mean squared error across the observed score range. And the shading is meant to be a sort of confidence limit on this. The purple line is what the combined system did. And what you can see here is that the combined system actually deviates from 16 examiners much more at the beginning, at the top and bottom of the scale. So it's actually, if anything, slightly more accurate around the pass mark in the middle, but it gets worse at the edges. And in a sense, this is because the training data isn't reliable there. It's the same problem you have with autonomous cars. If you are suddenly faced with a clown on stilts flying a balloon crossing the road and you haven't seen that in your training data, maybe you get things wrong and you crash into the person because you think the balloon is a cloud and the stilts you think are, I don't know, street lamps or something. It's the same thing here, that we don't see as much data at the edges, and where we do, the training data, which is only marked by 1 examiner, is much more variable, much less reliable. So I can show you this in a different way. So here, I've ranked outlier scripts. I've taken out the 300 in the middle that we're pretty accurate at. And the black scores, the black dots, are the training signal. The red dots are the combined system output. And the black lines are showing you the range of human examiner marks for 16 examiners. And what you can sort of see here is that even at the outlier stage, the system tends to fall within the range of human examiner marks. But of course, when you take the mean of that, that's a very hard thing to hit when the examiners themselves are deviating so much. So if I couldn't show all this on one side. If I showed you the middle, it's all compressed quite a bit, because in the middle you have a lot more data, and the examiners agree a great deal more. So I think with this, we've really hit about the limits of what we can achieve. And to do better, you really need to actually deploy the system and have the examiners, in a sense, remark or do active learning or something like that. So that's the end of the first part. I've told you a lot about summative learning. Yes?
Sorry, because I have to leave to ask a question. So it's very interesting that you try to go from correlation to causation by using some additional terms. So could you just say a few more words about how you can make use of multi-task formulation or write additional other functions to really derive the signal of causation?
Well, I mean, it's not, causation ultimately in this space is, somebody has a communicative intent and they produce some text. And if they're a good native speaker or a writer, the text achieves that. It achieves, you read it and something happens in your head, which says, you get some information, maybe you get persuaded, etc., etc. So causation, at a deep level is all about, what we do with language. But at a slightly higher kind of level, there are felicitous and infelicitous ways of achieving that with text. So if your text is very error prone, it will be hard for somebody to interpret. Maybe there are certain situations in which using modal verbs is the right thing to do, and others where it's not the right thing to do. So you want the system to look at that kind of thing, which is a manifestation of the underlying cause. I want to achieve something like tell you what's going to happen when you come and stay with me. So what we're trying to do is force the system into a space where it's learning broadly grammatical things, rather than just learning things like length, which are very salient to the signal. So I wouldn't go as far as saying we built in causation. Of course, if I could do that, I would be very wealthy, because I would have solved one of the major problems with the whole deep learning framework. We could be getting closer to being able to do reasoning and so on, as opposed to pattern matching. But what I've at least done is force it into pattern matching in the right kind of space. So, yeah.
Yeah, thank you very much.
Okay, so I won't go through this in as much detail, because I'm aware that we have to stop at 3, but I'll just tell you a little bit about this. So this is a much more common task in our field. There have been a number of shared tasks here, and the task is really to spot an error, detect it, and then correct it. The problem is the way the task is framed, there can only ever be one correction. And as I said earlier on in this talk, that simply isn't true for language. There's always multiple ways of fixing things. So here's some errors of some kind. And if I just pick one in the middle, like tense aspect, I like kiss you, I could correct it to I like kissing you, but I could also correct it to I like to kiss you. Either correction, and certainly out of context, looks absolutely fine. This is true for every one of these things here. So the task as it's framed is strange, because what you're given is a data set like the one I showed you with an error and one correction. But really what we're actually interested in is much more in detection and hinting to people that they might need to do something to this text for the application. But nevertheless, all the academic work has been framed this way. So people over time have tried a number of ways of doing this, but everybody has now converged on treating it as translation between a bad and a good version of a sentence, and also using transformers, like I talked about earlier. And then there's a toolkit that we built called Errant that types errors and will allow you to figure out whether a suggested correction is actually the same as in the data set that you're testing or evaluating on. And there's a bit of complication to that I won't go into. And then we evaluate in terms of precision, recall, and F0.5. F0.5 weights precision much more highly than recall. And the current state of the art is up in the sort of 70%-ish for ensemblers and about 63% for a single model. And that's quite good, given that the real probably, one's detection rate is probably higher than that. It's just that often the corrections, they're probably quite reasonable, but they're just not the ones in the data set. In the system, we use actually a model similar to the transformer, but based on a slightly earlier technology. We also use some rules, and we also use a sentence level grader. And so the rules look like this and are just extracted, induced from training data. If you see he wants to, you can suggest a correction once pretty reliably. And that gives you high precision, but very low recall. This is a sort of deep learning model. I won't go into the details, but essentially you're building contextualized embeddings again, which are good at predicting, what the next word would be, or what this last word should be. But then you're putting on top of that a feed forward level, and then a further level, which is softmax. And the softmax is just, is there something missing before this word? Is this word necessary? Does this word need replacing, or is it correct? So those are your labels. And that model gets you up to around sort of 56%. So it's not quite as good as the transformer, but it's still a lot better than the CRF, which is a sort of older style model. And what you can do with that, what you can do with the first level is you can make these kinds of suggestions. So if you hover over things, it says things like, is this the right word? Did you mean to write C, S-E-E, not C-E-A, because the context looks like it's a verb, not noun and so on. With the second level, you can just box words but not make suggestions. So with the LSTM model. And then finally, what you would like to do is, if you can't actually say there's a problem here, but the whole sentence doesn't look good, you would like to be able to brown it out in the interface. And the way we do that is we build another feature-based model. And we train it by taking the good and bad scripts that we can build from the corpus. And we use the overall score plus an estimated error rate, and then extract these features. And here you can see that the top lot are the good versions of the bottom lot, and you can see that the system is downgrading the ones with the errors in relative to the ones that have been corrected. So you can test it quite thoroughly like this. And basically what this means is that when it sees something with an error in it, it can't actually say specifically there's an error here. It can still say there's an error somewhere in this whole sentence. You need to look at this whole sentence again. And in the actual model, it can grade that too, but we don't use that in the interface. And finally, is this system good for people? Well, we've tested it with students, and they actually do use it. They do make revisions. The revisions on the whole make their performance better, so the scaffolding is working. Their feedback on the system, this was 2 trials where all we changed really was the user interface and user experience. So it's the same engine underneath. And basically they like the system, and this is the sort of thing they say about it, which they should have put through the system. The first one is, I like all the feedback and it helps me. And the second one is, why don't you tell me the answer? Which is what all students say. Not all students, but a lot. So what could we do to do better? Well, we're pretty much at the limits, I think, of what you can do with machine learning and NLP. But already there are people in this system. There are learners. And exploiting what they do more would be one way of improving it. There are also tutors in the system, because you can use it to set prompts for classes, and the classes do them, and the tutors give feedback. And if the tutors were giving feedback via the system, we'd be getting a signal. And we really need to train the examiners to take the system seriously and work with it, rather than to continue to score things all over the place. But that involves a change of work practices at Cambridge English. And the other thing about this system is it's not, particularly if you move to the neural network, it's not very interpretable. So you can't tell a student very easily based on the model, why they got the score they did. So recently I've been building some old-fashioned feature-based models that are more positive and say, you use this construction and this improved your score. And by construction, I can point to something and say relative clause. We would ideally like to be able to develop an interpretable neural model as well, because in the long run, they should be more easy to customize. There should be less work in it. And the problem relevance model, I haven't told you anything about that, but I'll leave you that just as a task. There is a problem relevance model in there. Now I've told you how we do the other bits. You have to figure out how we did that bit. Okay, well, thank you very much for listening. Here's some links to some papers, the Alta website, where there's over 150 papers on this general topic. Also, the company that produces Write, Read, and Speak and Improve. So there's also a read and a speak and improve, not just a write and improve. And thank you for listening, and I'm happy to take any questions that you have.
Thank you very much, Ted. Questions?
Does that apply to other languages, or this specific one?
There's no reason in principle why you couldn't do this for any language. I've been asked if I would do it for Welsh, which is a language that the Welsh government is trying to promote. They have a lot of second language speakers. You need a corpus, but they do have, not as good as this one, but they do have corpora. These days you can build parsers for languages very straightforwardly. So there's no reason in principle why you couldn't do this for Welsh, and you could do it a lot faster than we did it for English, I think. the two things you need are, a corpus which has some information about errors and a corpus that has some information about what level this writing is at. And then you can bootstrap, I think, from there.
Does it matter if the language like Hebrew or Arabic or Persian, they use the right to left?
I think scripts are problematic. They do raise problems, and we personally haven't worked on that. Well, at least not in this. With SwiftKey, we did a lot of work on Arabic and Chinese scripts and so on. There are NLP solutions to that out there. So you would have to take. So if you wanted to do Arabic, for example, you would have to look at those solutions. But again, for Arabic, there are data sets. So in principle, one can do this. It would be a bit harder, but
because I like the approach that you use here, and if it applies to other languages, that would be great.
Millions of people use Write and Improve. It's a quiet success. They've never really, the Cambridge English have never really marketed it very well, but it's used by millions of learners, or has been. At any one time, I forget what it's up to now. It's well into the hundreds of thousands. People typically use it for about 3 months before they take a test. So it works. They like it. And they should be pushing it, but they're not for all sorts of reasons. Yes, I think almost any language where there's a lot of second language learners, they're distributed, and they don't all have tons of money. Something like this is a potential good idea.
Who decides which is the correct English?
Well, yes. So the data set that we have was actually built by quite a good friend of mine who's a British English speaker from the south of the country. And so her early annotations were very much that was the target. But actually, at the time, Cambridge English sort of said, you're learning upmarket Cambridge English. Since then, it's been relaxed quite a bit because Cambridge English is now in South America and more in India, and was in China, but perhaps there's going to be much in the future. It's hard to tell because they've cracked down on language tutoring and stuff in China recently. So they've moved to a kind of more global model. But yes, that's an issue, right? And that comes back to this business about, I think you can say this is an error relatively reliably across. I mean, not if you're trying to teach a really sort of low prestige dialect like Black English vernacular or something. But if the idea is to aim for a more or less neutral kind of global English, spotting the errors isn't too bad, but correcting them is a real issue, which is why we focus much more on the spotting of errors and trying to scaffold people by saying there's an error here, think about it. And the suggestions we make are really quite conservative. And they would probably, you would find, be quite sort of tweaked towards British English. There are other funny things going on here because, I mean, it's all about colonialism and so on. You know, the Indians learn British English, but the South Americans learn American English. That's to do with who has most influence, where they get the courses from, and so on. I mean, that, I think, if we could do more work on the system, we would like to take all that out. And we would like to perhaps, one thing that you find is that people who speak different languages as their native language make different patterns of errors. And we would like to be able to tune the system to that and in principle tune it to whatever variety they're learning. The problem there is getting enough data to be able to do that well across the board. And since we're trying, I mean, millions of people use this, and now we're up to something like, it's well over 500 native languages. And obviously, there's a big sort of distribution on that, like a zip, long tail. But nevertheless, you want to kind of give them all a fair shot at it. And for the long tail, we just can't build anything bespoke. We could probably build something bespoke for Spanish, a few other languages, Mandarin, things like this. But then you get into probably just don't have enough data about the kind of errors people make. We would, if this was online and it was capturing data from everybody, and that data was being processed in a scalable way. At the moment, there's a small team of people who annotate that data by hand. That's just not scalable. So we just won't get enough data that way. But it's at the point now, you see, when Apple launched Siri, it was rubbish. But they also put it into a framework where they were getting feedback all the time and actioning on that feedback. And that's the difference between companies that know how to do this stuff well and everybody else. And unfortunately, Cambridge English is not one of those companies. It's not Apple or Google, and they're still coming to terms with, you know, just the whole idea that they might mark a script automatically, and that might actually work. So turning them into an analytics company that can really scale something like this, you know, that's going to take a few more years. And who knows, they may not be around by then because Duolingo may have wiped them out.
Thank you. Time for one last quick question. I don't know if it's a quick question, but morphology. So, not a lot going on in English. What would this look like if you were dealing with perhaps not a polysynthetic language, but you know, well, a language like Arabic, say, where there is more morphology going on?
Well, I'd have to extrapolate from my days of learning Latin, but you know, one can easily end up with the wrong ending on the wrong stem. And I assume that I know a little bit about Arabic, and I guess that more or less carries over, but it's you know, it's obviously a very different language. So one can process a word. In fact, there are, in terms of the academic work we've done, not what's deployed in Write and Prove, we've actually done quite a lot of work on models that actually take a sequence of characters as input, because that helps you deal with things like spelling errors much more robustly. So I think you'd go that route. You would use probably a dual sequential model, one that worked at the character level and then at the word level, and combined information from the two in the way that some of these deep learning models do at the moment. If you wanted something more interpretable with better feedback, you'd probably have to go back to the old-fashioned kinds of things that we used to do with finite state machines and so on. But I think in principle, it's not really that different. It's just you're working at a different level.
Wonderful. Okay. Well, thank you again, Ted.
Thank you.